Does that make sense so far? Okay, so from outermost coming in, thoracic cavity wall, which is your ribs and your muscles in there, we would then encounter your parietal pleura first. Then you would encounter that serous fluid between the two layers. And then you would encounter that visceral pleura. Visceral pleura is like shrink wrap on the lung. So if you keep going any deeper in, then you're going to be in lung tissue. We're going to ignore the picture and talk about what's written here. You've probably heard of pleurisy before. Pleurisy is an inflammation of those pleura. So if they become inflamed, instead of lubricating and gliding past one another, those membranes can actually become swollen. So instead of gliding, they're rubbing past one another. Pleurisy can cause dull or sharp aching pains every time a person breathes. So people with pleurisy may experience problems breathing. Every time they breathe in and out, they have a stabbing pain in the lungs. So oftentimes it comes from things like pneumonia or infections in the thoracic cavity that really irritate that lining. How do you get rid of pleurisy? Stop breathing?
Steroids or...
In time.
Time, yes. Steroids, take some time, and antibiotics are probably the ways to get rid of that pleurisy. So pleurisy really is, you've got to solve the root of the problem, which is typically an inflammation or an infection in the thoracic cavity. Yeah. It may be pneumonia or any kind of irritation or inflammation infection that's in the lungs. The next disorder up here I want to mention to you is pneumothorax. Pneumothorax is the introduction of air into the pleural space. In order for your lungs to inflate properly with air, the pressure inside your thoracic cavity has to always be less than the outside of the environment. It's got to be negative pressure inside your thoracic cavity. If a person is stabbed or cut into the thoracic cavity and it penetrates into these pleura, you now create pressure inside the thoracic cavity that is going to attract air to enter into that area. So in that case, the lung will collapse, and that's a problem that we call what?
Atelectasis.
Atelectasis, right. So a collapsed lung can result from pneumothorax. Atelectasis, of course, would make the pressure changes in the thoracic cavity such that the lung cannot stay inflated. So how do you solve a problem like a collapsed lung? Exactly. Get the air out of the thoracic cavity, seal up the hole or whatever's causing the air to be in the thoracic cavity. That way the pressure can become negative inside your thoracic cavity, making sure the lungs stay inflated. So you're right, get that air out of the thoracic cavity. If you're interested in seeing how pneumothorax actually works on your IT10 CD, they do show you an animation of taking a scalpel and penetrating into the thoracic cavity, and then there goes that lung. It shrivels up just like a balloon that's let all the air out. And finally, one that's not on your homework list, but I wanted to mention it to you anyway. Pleural effusion is excess fluid in that pleural space. So between the two serous membranes, between visceral and parietal layers, we know there's supposed to be a certain amount of fluid, that's that pleural fluid, but this is excess fluid that's between those two layers. What do you think excess fluid does to the capability of the lungs to fill with air? Makes it more difficult, right? Because it's like putting pressure on the outside.
I worked at ER 5-9 and then for CDC that came in and had a 6-hour wait and had 2 days. He had full diffusion.
Wow.
And through the fluid, I had 3 liters of fluid in one lung.
Wow. I'm surprised he could breathe at all.
His oxygen actually desaturated because his body compensated.
Wow.
And it actually took a while for it to come back up once we did the fluid.
Did he come in because he had trouble breathing?
There was some pressure in his chest. We thought he was in the heart failure, but the CT showed it was full of effusion. So
Wow.
we laid him on his stomach and he holds it, it's a sterile procedure. There's a line that runs down into a drainage bag, and you have to literally suction it off, and he's awake the whole time.
Oh, man.
And it's like an amber color, fluid.
So it's got a little bit of blood in there, apparently.
Yeah, because and I'm sure they did a lot of tests, but I don't know what the results were, because I was only there 8 hours, but there's something else going on. 3 liters of fluid on one side.
That's amazing. It's a surprise he was able to breathe at all with that much fluid. Wow. I mean, considering that we have 5 to 6 liters of blood, yeah, that's amazing. All right, so just want to share a little bit about that stuff with you. And like I said, pneumothorax is on here for you, so if you'd like to see how it works, take a look at your CD. Okay. That information is actually on the top of page 77, and that will take us now over into the physiology. And the physiology starts on page 78 for you. How about questions so far?
Yeah, what can I find on page 77, the pathway of
You know what? If you start back at the beginning of this chapter, everything's in the order for that. Yes, if you start back on 73, everything's in bold, and you'll have to flip the pages and just trace it on down, and I can check it for you if you want. All right, so we're going to talk to the rest of the class today about physiology of the respiratory system. So we're going to start off with gas exchanges, and of course there's 2 processes of gas exchange in our bodies. One of those gas exchanges occurs in the lungs, and it's a process we call external respiration. Why external? What does that imply?
Getting rid of carbon.
Well, it's cells and tissues of the lungs and the outside air. So the gas exchange in the lungs is external because we're exchanging gases with the external environment. So the whole point of exchanging gases is to get circulation of oxygen into our bodies, and of course to get rid of CO2. Where in the body do we need oxygen?
Mitochondria.
Mitochondria, yeah. Every cell and tissue that has mitochondria needs oxygen because oxygen is one of the fuel ingredients to make ATP. So interesting how the process of respiration, in terms of our gas exchange here, is actually providing that O2 that we need for mitochondria to make ATP. So it's not just a cellular event, it's actually an organelle event that we're providing our body with these gases. All right, so let's take a look at the 4 events a little way down your page there. There's actually 4 processes to the process of respiration. The first process is called pulmonary ventilation. Pulmonary ventilation is breathing in and out, what you're currently sitting at your desk and doing. As your lungs inflate with air and deflate as you exhale, that is simply pulmonary ventilation. You might say that pulmonary ventilation is 2 events, inspiration or inhalation, which is bringing air in, and exhalation or expiration, which is pushing that air out. We'll talk about how that works in just a moment. The next of the 4 events that happens in our bodies in terms of respiration is the one we just mentioned. External respiration is a process that occurs in your lungs. This gas exchange provides an opportunity for oxygen to get into our bloodstream and what to move out?
Carbon dioxide.
Carbon dioxide or CO2. We call it external respiration because we're exchanging gases with the external environment. So the external world comes into contact with our bodies in these alveolar air sacs. Let's talk about some of the terminology there on page 78. You'll notice under 2C, it says how are these gases transported in the blood. You'll notice 2 terms there, loading and unloading. This is just like taking a trip. If you're loading your car, you put things in. If you're unloading it, you take things out. I'll be right back.
Isn't that a pretty picture? Isn't that a pretty picture? Just feeling in time.
Okay, let's take the picture on the left for just a moment. This is a complicated mess that we're going to get into later on an acid-base discussion. That's going to be a later chapter for us, but at least it gives you a sneak preview of where we're going, right? In the lung, notice where we're at. This is a pulmonary capillary right here. Right here is one of your alveolar air sacs. In the lungs, we're breathing in air that contains a lot of oxygen. So the oxygen is going to diffuse from the alveolar air sac here into the pulmonary capillary. So we say that oxygen is loaded into the bloodstream because we're moving it from the air into the blood for transport. That's what happens at external respiration, is the loading of oxygen. Carbon dioxide, you'll notice this complicated mess of a reaction here. Carbon dioxide is actually going to get moved from the bloodstream where? Out. So we diffuse it here into the alveolar air sac, and of course we can get rid of that carbon dioxide the next time we exhale. So we say carbon dioxide is unloaded since we're going to remove it from the bloodstream and place it into the air. I like this picture because it's real simple and you can see how easy it is for gases to diffuse. This time the picture's flip-flop. Up top now is your bloodstream. There's your capillary in the lungs. This time the alveolar airspace is down here. I want to show you this one because you can see here's the lining of surfactant inside the alveolar air sac. This is alveolar epithelium. They should have just said it's simple what?
Squamous.
Simple squamous. Right here is fused basement membranes, and right here is endothelium of a capillary. Well, capillaries have only one cell layer made up of what?
Same.
Simple squamous. Good. So you can see how easy it is for diffusion of gases to occur. If you're moving into the bloodstream, we are loading that gas, and of course all we're doing is moving across surfactant, simple squamous, a fused basement membrane, another layer of simple squamous, and boom, we're right there into the bloodstream. Which gas moves from the air into the bloodstream? Oxygen, good. Which gas is in reverse, coming from blood to the air? Carbon dioxide, good. So you can see it's a real simple process since we're only moving across one cell layer thickness. Alright, let's go back a minute. The next thing on your worksheet, number 3, there talks about respiratory gas transport. Okay, this takes us back to chapter 18 for a moment. Pulmonary capillaries join with pulmonary venules. Pulmonary venules join with pulmonary veins. Where do pulmonary veins take you? Left atrium.